Okay, hello everyone. So welcome to the second session of the MolVA for today. In this session, we will have two talks or two paper talks, and then in the end, we will have an invited talk given by Barbora Kozlíková. So we have a really nice program to look forward. And I would like to kick it off right with the first talk, which will be given by the Robin Maack, and it's about the framework for uncertainty-aware visual analytics of proteins.
Welcome to the presentation of the paper, A Framework for Uncertainty-Aware Visual Analytics of Proteins. I'm Robin Maack presenting this framework created in collaboration with Michael Raymer, Thomas Wischgoll, Hans Hagen, and Christina Gillmann. So in the field of molecular visualization, data originates from a variety of sources like X-ray crystallography, nuclear magnetic resonance spectroscopy, cryogenic electron microscopy, or even molecular dynamic simulations. All of these approaches introduce some form of uncertainty due to their experimental nature. In these cases, we're talking about positional uncertainty of atoms most of the time. It was shown that uncertainty should be visually communicated in visual analytics applications, resulting in a clear need to represent the positional variation of atoms in protein visualizations. Our approach to deal with this necessity is an application that uses three components that show the underlying uncertainty of a protein at various levels of abstraction. The volume view gives a direct visualization of the protein geometry, surrounding it with an isosurface that can be adjusted to the liking of the user. Ramachandran plots show the distribution of dihedral angles of all amino acid residues of the dataset. The angle combination uncertainty is visualized using isolines in the Ramachandran view. When selecting an amino acid residue in one of the views, it gets highlighted in both views and additional parameters are shown in the statistics view. The selection process therefore connects the three views, making them appear as one unit. After this quick introduction of the application, let's talk about the structure of this talk. First, we will define what is meant by uncertainty, defining some basic variables needed to understand this underlying concept. Then, available values in those datasets that can be treated as uncertainty are reviewed and propagated to show their influence on protein properties. After the uncertainty present in the data is clear, we will look into the goals that should be achieved using this additional data. Also, general requirements will be explained. To make use of the uncertainty information, a scalar field has to be computed first. For the visualization side, the 3D volume view and its implemented protein representations are provided, also showing how the level set and scalar field generation changes when using different geometries. The Ramachandran plot and variable nomenclatures, meaning its background map, are represented next. Following that, the statistics view will be briefly introduced, also talking about the interaction modality. To give better insight into the tool and its workflow, a short demonstration will be given. Finally, the talk will be concluded and future work is presented. So let's talk about what uncertainty is and how to get useful information out of it. Therefore, we plot a measurand taking a snapshot of an object in space. But there's a problem here. When measuring any kind of data, you will not end up with the true value most of the time, but with a value that is usually near the true value. The distance between the measurement and the true value is called the error of the measurement. In most cases, you will not have a real value and therefore can't measure the error itself. This is where uncertainty comes into play, helping to provide a sense of how correct the measurement is on average. Therefore, we usually get some value u out of the data, defining a range around the measurement in which the real value should reside in. If such a value u does not exist, the uncertainty has to be quantified, meaning that we take a thoughtful guess using various statistical models. Independent of the uncertainty quantification process itself, the real value can also reside outside the uncertainty range, which has to be captured too. To do this, probability distribution functions can be used to create a smooth function that describes the probability of the real value residing at a specific location. Then, level sets can be generated using a set of uncertainty values. Modern methods for protein structure determination, including X-ray crystallography, cryo-EM, and NMR, can provide three-dimensional structures of soluble polypeptides with relatively high confidence. The resolution of these structures is sufficiently high that the location of individual protein and ligand atoms can, in many cases, be determined with precision up to a few angstroms. Here, several sources of uncertainty are related to these atomistic positions, as proteins are not monolithic, rigid molecules. Even with the context of protein crystals, so when we force them to live within a fixed crystal structure, local protein regions are subject to thermal mobility to differing extents. For our project, we focused on two sources of uncertainty. First, most PDB files provide a so-called B factor, also called heat factor or Debye-Waller factor. It describes an isotropic distribution of the atom's equilibrium position, meaning that the uncertainty is the same in each spatial direction. The second source of uncertainty comes from multiple conformations of the same protein that were captured or simulated. Therefore, each atom in a protein has a set of positions it can be found in depending on the model used. To get the distribution of an atom in such a dataset, we decompose it into eigenvectors and eigenvalues, where the eigenvector with the biggest eigenvalue corresponds to the direction in which most of the atoms deviate from the average position. As eigenvectors are linearly independent, we can use them to create a standard deviational ellipsoid, as shown on the right. Here you can see an excerpt of a protein with a complete amino acid residue in the middle. For each of the amino acid residues, two important angles, namely phi and psi, can be found. The two angles of an amino acid residue are then plotted on the so-called Raman-Chandran plot, representing each angle combination as a dot. An example of such a plot for a complete protein can be found in the bottom middle. So let's focus on the psi angle here, highlighted with red rectangles. You can see how this dihedral angle measures the angle between planes spanned by two crane triangles. These two triangles depend on four atoms, which can be set about any of the dihedral angles. So to measure uncertainty, we have to consider the available information of those atoms and use them to calculate uncertainty measurements. In the case of an available B-value field, we can simply use the average of the B-values. For anisotrope datasets, again, we have to use eigendecomposition to get the two major axes of distribution. Those can be shown as standard deviational ellipses. Now that we saw the available uncertainty information of the dataset, we should talk about the goal that should be achieved using this information. First, the positional uncertainty should get a proper representation such that the user can get a feeling for the magnitude and direction of distribution. Also, suitable molecular representations should be implemented to give the user a familiar working environment that is just extended with additional uncertainty information. While extending these representations, visual clutter should be avoided as much as possible, not including information that could be seen without this additional uncertainty information. Insights taken from the visualization should be verifiable to give the user more information to be used in further investigation of the dataset. To have a simple extraction of information, the views in the application have to be connected, providing the user with a tool that acts as one unit. As we just saw, the first goal is to visualize positional uncertainty, and as we also just saw before, we want to create isosurfaces for that reason. Therefore, to extract isosurfaces, we need a basic data structure to extract it from. In this case, we create a scalar field with certain properties such that it only has to be created once for an arbitrary set of level sets. To do this, we need a distance metric that supports scaling. To start, we have the distance between the ellipse center, meaning the atom center, and the center of a scalar. As we want to know how far an atom is away from a scalar under a directional distance, we first have to define a unit distance. Therefore, the user can later choose if he wants to see the uncertainty field at a distance of 1 standard deviation or 3 standard deviations, for example. This distance depends on the underlying standard deviational ellipse, the van der Waals surface, the eigenvectors, and the two endpoints. So first we calculate the intersection point denoted as I and measure the distance of it to the van der Waals surface. This tells us the directional standard deviation called sigma d, meaning that we created a directional unit distance vector of standard deviation. Now the distance between the van der Waals surface and the scalar center can be divided by this unit vector, retrieving the final distance in terms of directional unit distance. It should be noted that sigma d degenerates to the root mean squared deviation in case of an available b value. Now this distance metric we just saw has to be used to create the scalar field. So let's have a look at the basic algorithm for all the protein representations. First, a KD tree is filled with the center positions of all atoms in the dataset. Then, it is used to find the n closest atoms to a scalar center. We have to do this as each atom has a different radius and uncertainty space, and therefore the closest atom in terms of directional distance sigma d is not trivial to find. When going over the n closest atom positions, the lowest distance to the scalar center, measured with our distance metric, is found and set as the scalar value. The 3D volume view is highly adjustable and almost all settings can be combined with each other. On the top row we can see the standard visualizations that are implemented. A shows the ball visualization with the atom element color coding. B shows the ball and stick visualization using the B value color coding. C uses the solvent accessible surface with a color coding extracted from a Raman-Chandran map. And D shows the ribbon model with the ribbon model color coding. It should be noted that any color coding can be mixed with any visualization, and that new color codings can be added by the user, providing a Raman-Chandran nomenclature that will be converted as shown in C. The bottom row provides techniques where uncertainty is shown with the existing geometry, while the amino acid color coding was used for all visualizations. E utilizes the superimposed ribbon model that provides all models at the same time, combines it with the gray uncertainty hull. If the user wishes to color code the hull with p-value colors, he may do so as shown in F. G shows the mini visualization that is only available for multi-model datasets, where the average position is shown with bigger spheres, and all available atoms for all models are shown with small spheres. This visualization can also be used to understand the data distribution better. Enabling it together with the uncertainty hull as depicted in H, it can give a direct explanation for the high uncertainties in the affected regions. The Raman-Chandran plot is always enhanced with the available uncertainty information. It surrounds the data points with isolines. In the isotrope case, you can see the axis-aligned ellipses that look mostly like spheres, as both angles share 3 out of 4 atoms and their root mean square deviations are just averaged. It can already be seen that the uncertainty is lower in regions that are on or near one of the core regions, while the core regions are anything that is not yellow here. In the anisotropic case, the distribution of dihedral angles is reviewed, resulting in mostly non-axis aligned ellipses. In this dataset, it can be seen that the alpha helix region is mostly stable, while all other regions are heavily changing throughout the different models. By the way, is anybody else seeing a rabbit with thought bubbles here? Well, anyhow, you can create various background maps called nomenclatures for the Raman-Chandran plot and load all of them at the same time. We can already see 2 different nomenclatures here. You can then change the Raman-Chandran nomenclature as you wish and also use a color coding extracted from it in the 3D view, coloring all the atoms of the underlying amino acid residue in the color of the region in the Raman-Chandran plot. On this slide, the statistics view for isotrope models can be seen on the left, as well as for anisotrope models on the right. Here a glycine amino acid was utilized. The top part of each statistics view contains general information about the residue, like its ID, dihedral angles, minor and major eigenvalue regarding the dihedral angles, its Raman-Chandran region in the selected nomenclature, the secondary structure, and the chain if it's a multimer. After that, a list of atoms is shown providing its element, ID, eigenvalues, or b-values sorted by strength. All values that can be expressed in a relative way are also displayed with their relative value next to them. This way, it is much easier to compare various residues and atoms. All in all, detailed information about the atoms and the amino acid residues in the dataset are available that way. The interaction modality is very basic at the moment, still giving the user the possibility to correlate all three views with each other. The user can select the residue in the 3D view or in the Raman-Chandran view to see the selection in all three views at the same time. Right-clicking fixes the selection to allow other interaction with the views while keeping the selection. But to actually show the interaction, let's have a look at the short demonstration. Here we are in the application with the 1GO3 dataset loaded. The protein was extracted from the HTLV1 virus that can cause leukemia or neural disorders. This NMR dataset contains 20 models that show different conformations of this protein. When loading the application, the average model is shown first, meaning that the average position of each atom is shown over all 20 models. The user can now look at all the models one by using the model slider. So the problem here is change blindness, because looking at each model one by one, you can't really grasp how the distribution looks like. Even when using superimposed models, this doesn't get better. To tackle this problem, we can use the isosurface we were talking about, as it allows us to see the distribution of the atoms as a summarization. To do this, we check the Show uSurface checkbox, set an opacity, here use 25%, and update the visualization. As we can see, regions with high uncertainty are clearly visible in the visualization as they have higher distance to the geometry. Still, the original structure is visible. If needed, the isosurface can be b-value color-coded to give an even better sense of the uncertainty space. But this comes with the cost of losing a clear view at the color coding of the underlying representation. So let us go back to the gray isosurface for now and have a look at the interaction modality. To check the assumption that the top part of this protein is actually very uncertain over all conformations of this protein, let's select the residue and give it a deeper look. Using the camera, the strong distribution in two spatial directions can be seen. In the Raman-Chandran plot, we see that its dihedral angle combination drastically changes considering all models. Let's further investigate the source of this uncertainty in the statistics view. Here, it can be seen that this uncertainty is present throughout all atoms of this residue. Especially atoms at the R group of the protein are affected. This can be checked using the mini visualization to show the distribution of all models. We see that the R group atoms are changing the most here, proving our assumption made in the statistics view. Selecting a value of 1 sigma shows that the isosurface actually represents the location of the core group of atoms in this residue. Increasing sigma d to 2 already encapsulates most atoms with a hull. A value of 3 encapsulates all atoms. This makes these 3 sigma values the most interesting in most cases and shows that the isosurface can summarize the spatial distribution of the atoms effectively. After this demonstration, let's have a look at the goals from the beginning and how they were fulfilled. First, the uncertainty can be shown in all available protein representations. Also, 4 very common protein visualizations are provided, such that a familiar working environment is presented to the user. Third, visual clutter can be avoided, giving the user control over opacity and color of the isosurface. Also, each representation can be restricted to only show its background atoms, further improving visibility. Users can also investigate the data at 3 levels of abstraction using the 3 views provided. Their interaction modality allows the users to always correlate the data selected, and the statistics view allows implicit comparison using the relative values. In the future, we want to either integrate our code into an open source project or create our own open source project, rewriting the code and adding more features. Especially a more flexible render control should be created to enable showing ligands and proteins in different representations at the same time. Comparison visualizations are another important goal for the future, as this can further improve the usage of the tool in production environments. As we saw before, currently only isosurfaces can be used to display uncertainty. For the future, we want to work towards incorporating volume rendering with transfer functions, for example. More interaction modalities should further improve user experience, and a larger set of standard visualizations will enhance the usefulness. So, this wraps up this talk. Thank you for listening, and feel free to ask any questions or recommend features you would like to see in an enhanced version of this application.
Okay, thank you, Ruben. This was really interesting talk, and I enjoyed it quite a lot. If there are any questions for Robin, please post them to the Discord or YouTube channel. We already have one question from Martin Falk, and he's first commenting that he also enjoyed the talk, and then he's asking whether there is a particular reason in the multimodal Ramachan plots for the Rentgen regions with rounded corners, or are you considering the different peptide types in the plot?
Okay, so I think like the rectangular regions, these are actually the nomenclatures. So what I did there is I used 2 different nomenclatures, but the thing is you can change them as you like. Like you basically only have to take a nomenclature you find on the internet, you put it into different regions, like you only have a black and white image for each region, and then you compose it in like a TXT file and give each of them like an RGB value. That is like that you can basically create your own nomenclature. So there's no real reason why I chose these in this example.
Okay. I also have one pressing question since I've seen your presentation before.
Mm-hmm.
I'm still wondering where the rabbit is within the chart. So maybe you can post a picture into the Discord channel for all of us to also enjoy it, because I was looking for it for a few minutes and I couldn't find it.
Yeah, like it was weird. Like when I was showing people the plots, some of them pointed out that in the right side, in the top region, there is basically something like a rabbit because there are like 2 ears, and then there are like thought bubbles going out, and it was weird. So I thought I asked people if they also see it. I can send a picture into the Discord channel later.
That would be great. Okay, thank you very much for the talk. Like I said at the beginning, it was really interesting. And I think now, in the interest of time, let's jump for the other talk, which will be given by the Alexei Abrikosov, and it's about topological analysis of density fields and evaluation of segmentation methods. So, floor is yours.
Hello, my name is Alexei Abrikosov, and together with Talha and Masood, we are going to give a talk about the topological analysis of density fields and evaluation of segmentation methods. Let us begin by asking a simple question. What is an atom in a molecule? The usual way to represent a molecule is by using the so-called ball and stick model where atoms are modeled as balls and bonds as sticks. In this case, in the case of water molecule, the oxygen atom is a red ball and the hydrogen atom is a white ball. But this way of representing a molecule ignores a lot of its properties. For example, it doesn't take into account the electronic structure of the molecule. A common way of visualizing the electronic structure is by utilizing isosurfaces. But as you can see here, depending on the choice of your ISO value, your visualization of the electronic structure is quite different. But why is it important to analyze electronic structures and electronic charge densities? Well, first of all, you can find out a lot of physical properties, and also you can use it to do bond analysis. For example, if you want to know if it's a covalent or a non-covalent bond. Problem is, as you can probably see quite clear, is that if you have a cloud, basically, it is very hard to draw borders between atoms, and it is an open question which has not been solved to this day. So, if you look at the way domain experts describe the molecular world, they do it in two different ways. They use quantum mechanics, mostly for like single atom and molecules, maybe crystal calculations. In this case, they're taking the electronic structure into account. They're solving the Schrödinger equation. This type of methodology is limited to a few atoms, and you get atomic or material properties from these types of calculations. And then you can use these properties, which you gain from the quantum mechanics calculations, and use it as input for classical mechanics calculations. These calculations utilize classical equations, and many atoms can be used in these calculations, and you get both properties. For example, if you have a whole bunch of CO2 molecules, you can run classical mechanics and see how they propagate, for example. Unfortunately, for us, the quantum mechanics cannot determine these two properties, namely the charges, which are used in this equation. The closest thing to charge, which you can get from quantum mechanics, is charge density. And over the years, there's been a lot of methods that were developed which try to solve the issue of determining charge. But not all of them are good or accurate. There have also been some rules that institute what a good analysis should have. The first thing is that it should be applicable to both periodic and non-periodic systems. It should give accurate electrostatic descriptions, and it should be independent from the method that determines the electronic distribution. So, to summarize the problem, we have a cloud. We have a method which determines the charge density in this cloud, and you have some overlap of the charge density between the atoms. And we want to see how you can divide these areas between the different atoms. One way to do it is to use either gradient or geometric segmentation methods. The gradient methods have the advantage of having a mathematically determined borders, and geometric segmentation is based purely on the proximity of a given point to the atomic position. Here is an image. We can see the gradient of an electron density. As you can see, you have these low gradient areas and high gradient areas. So the idea behind the gradient-based methods is that if you are inside, for example, this region, if you take any gradient point here, you can follow then, you take any point there, you can follow the gradient to the maximum. Unfortunately, most codes, chemical codes, work with the so-called valence charge density, which is only the outer electrons. And because they're using valence charge density, they have a huge hole at the atomic positions. So instead of going to a single point, you will end up on this ring, for example. And this will greatly impede the segmentation process. On the other hand, if you're using full charge density, and some codes are able to generate the full charge density, you'll have an easy time of determining the segmentation because it's, like I said, it's easy to get to the all the points will end, all the gradient paths will end up at one point. So there we have the solution. We take our data, which is a scalar field. We determine the atomic volumes using a segmentation method of choice, and then we sum up all the scalar values so that the total charge of an atomic segment is just the sum of all the scalar values. The drawback of this approach is then that it's not necessarily that the electrostatics is satisfied by this. And this is what we mean. You only have a huge charge density, which occupies a big volume, and then you approximate it as a point charge. And if you look at it from a long distance, it's okay. But if this distance is short, the description is no longer valid. And to fix this, what people do is that they utilize the multiple expansion, which means that your volume, charge density volume, is now described as several different electrostatic descriptors, namely charge, dipole moment, quadrupole moment. In practice, it is fine to go. It's fine not to go beyond the dipole moment because, as you can see here, the quadrupole moment decays as 1 over R5, which is very fast. Now, the data that is being analyzed is generated by VASP and Gaussian DFT software packages. Two types of density fields are considered, so namely the valence charge density and the full charge density. The scalar fields provided as cube files or charge card files, and the systems that are being analyzed are H2O, benzene, PNA, NaCl, CO2, and copper. In our talk, we mostly focus on the H2O, NaCl, and CO2. The segmentations that were considered are the discrete, Morse-Mail, Henkelmann's pattern analysis, TOPOMS, and Voronoi. So what are the results of the analysis? Here is the charge determination of a Cl ion in an NaCl crystal. As you can see, most of the methods are giving quite similar results, except for the TOPOMS for the full charge density, because the full charge density is a very bad data set for describing the electronic description of that data set is very bad. So that's why we see it being so big here. On the other hand, as we can see here, the full charge density is perfectly fine at describing the volume of our atoms. The problem, of course, TOPOMS has also some problems with low grid resolution, and then it has a puzzling drop in its ability to determine volumes at 200 grid size. And the other thing which we try to analyze and determine is the dipole moment in the CO2 molecule in a molecular crystal of CO2. In this case, the properties which are known is that the oxygen steals electrons from the carbon and you get a dipole moment along the bond between the oxygen atom and the carbon atom. Just as a quick rule of thumb, you can see that what we expect that all the atoms, all the dipole moments should be uniform, both in size and its direction. And that is true for both the numerical and the Voronoi, although in Voronoi, we see the puzzling thing of it pointing in the opposite direction, which is a hint that the position of the segment matters. And then if you look at the discrete mass, you see very bad behavior, mainly because the behavior between the different molecules is different. So you have a very big dipole on one molecule, so namely this one, which is this one. Because of periodicity, it's hard to see, but this one and this one have a very large dipole moment. And then these dipole moments on the other molecules don't really point towards the carbon anymore. But we will talk about this more in the comparison section. And now Talha will take over and go over the comparison.
Thank you, Alexei, for providing a nice introduction. I will now provide the comparison results for various segmentation methods. I will be giving a more data analysis and visualization perspective for this problem. We consider 6 different datasets for this case study. 3 of them are molecules, while the other 3 are periodic crystal lattices. The data for the molecules is generated using Gaussian software, while for the crystals we use WASP. We choose 3 different types of crystals. One of them metal crystal, which is copper crystal here. The second one is a crystal for monovalent salt. It has ionic bonds. While the third one is a crystal of molecules, which is represented by CO2 crystal here. This allows us to evaluate the segmentation methods on a variety of charge density fields. To recall, we use 5 different segmentation methods in this case study. Some of these methods have been developed in the domain of computational chemistry, while some are from the visualization domain. Have a look at the charge density for H2O. The maxima in this charge density field correspond to the atomic centers. The gradient-based methods consider the gradient of the charge density field. We can show the streamlines corresponding to this gradient field. You can observe the separatrices in this gradient field. The separatrices divide the field into different regions depending on where the streamlines end. So each streamline ends on one particular maxima among these 3 atoms. So this results in a segmentation something as shown here. Both discrete gradient method and the numerical gradient method use this approach. The discrete gradient method, we use the topology toolkit for this purpose. For numerical gradient approach, we use Hankelmann's Bader analysis and another recent work by Bhatia and others, which is a software called TopoMS. We also compare against geometric approaches. For this, we use Voronoi-based approaches, both Euclidean and weighted Voronoi approaches. The key idea in this approach is to divide the region based on the proximity to the atom centers directly without taking into account the charge density. Now I will talk about the evaluation of the segmentation obtained using these methods. So for molecular datasets, we can use direct visualization of the atomic segments for a visual comparison. This provides a more qualitative comparison of the methods. Let me discuss the visual comparison for one of the molecules in more detail. So notice the asymmetric segments obtained in the discrete gradient approach. So on the left, you can see for the carbon atoms, we have very jagged boundaries and asymmetric regions. For the numerical gradient approach in the middle, so the Henkelmann and TOPO-MS based approaches result in very symmetric segmentation, at least for the 4 carbon atoms. For Voronoi based approaches, the separation boundary is very planar, and the weighted Voronoi approach is closer to the numerical segmentation approaches, but there is still a difference, especially at the carbon-nitrogen bonds. The qualitative visual comparison is good, but it is not enough. So I will talk about some quantitative measures for comparing the similarities and differences between various segmentation methods. However, I would like to emphasize that there is no ground truth available for the segmentation. So we use Jaccard coefficient index to study the similarity between two methods. So Jaccard index is a well-known method for quantitatively comparing the overlap between two sets. It is the ratio of the size of the intersection to the size of the union. In a dataset, for a given atom, we obtain two different regions. So we can use Jaccard similarity index for comparing their similarity. So we call this similarity as volumetric similarity of the regions. We also compute something called charge similarity, where we integrate the charge density within the intersection region and the union region to obtain a charge similarity score. So usually we observe charge similarity to be higher than the volumetric similarity. We visualize the quantitative comparison for a pair of segmentation methods using two methods. Firstly, we use the direct visualization of two segments and their symmetric difference in 3D as shown here. Secondly, we use a 2D glyph which shows the Jaccard coefficient and the dipole moment in a combined figure. So the Jaccard coefficient for charge and volume comparison are shown as bar charts, while the two arrows at the top indicate the dipole moments. So in this case, we are showing the regions computed for one of the oxygen atoms in the carbon dioxide crystal lattice using the discrete and numerical gradient approaches. So notice that although there is not much difference in the charges, there is some difference in the dipole moments, and especially in the direction of the dipole moments. So in the case of numerical gradient-based approach, the dipole points correctly along the direction of the carbon-oxygen bond, while for discrete gradient approach, this is not true. Now let me discuss another visualization challenge. So for a given data set, we have multiple atoms, and like I mentioned, we have at least 5 different methods to compare against. So there are lots of combinations of methods to compare. So we use a comparison matrix for this visualization challenge. Along the diagonal of this matrix, we show the computed atomic regions in 3D, as shown here for 3 approaches. Above the diagonal, we show the symmetric difference between these regions. And below the diagonal, we show the 2D dipole comparison glyphs, like this. So, especially here in the 2D glyph, note the completely opposite direction of the dipoles for the numerical and the Voronoi based approaches. Now, for a given dataset, to represent the summary of the volumetric and charge comparison based Jaccard similarity scores, we again use a comparison matrix. On the diagonal here, we show the charge and volume tables for all the atoms in a given dataset. Above the diagonal, we show the Jaccard index based volumetric similarity scores as bar charts. The color of the bars is based on the atoms. The dark gray bars correspond to the carbon atom, while the red bars correspond to oxygen atoms. Below the diagonal, we similarly show the similarity score based on charge, the charge similarity score. Let's focus on two methods, namely the Topo-MS and discrete MS approaches. Notice the high degree of similarity for oxygen, but not much agreement on the segmentation for carbon. Also notice, so for one of the carbon atoms and two of the oxygen atoms, the similarity score is lower than the other atoms. So this is largely because of the asymmetry in the discrete MS approach. To summarize our comparison based on these datasets, here are a few key observations. The numerical approaches, namely TopoMS and Henkel-Men approach, they result in similar segmentations. For metal crystals, all segmentation methods agree on the atomic charges and the volumes. For ionic crystals, we noticed that the gradient-based methods differ from the geometric methods. Further, for molecules, we observed that there is a larger difference between the discrete and numerical approaches. Finally, to conclude, I would like to end with two takeaway messages. Number one, accurate geometric segmentation matters, especially for the segmentation of charge density fields. Topologically correct segmentations and molecular graphs are not enough, and we need accurate geometry, especially for computing higher order moments. However, the choice of segmentation methods depends on the data and also on the application. The discrete gradient-based approaches are topologically correct but have geometric inaccuracies. The numerical approaches, on the other hand, are geometrically correct but more expensive and more sensitive to noise. The geometric approaches are fast and efficient, but we observe that they need proper adjustment of weights to work better. Lastly, we would like to acknowledge Dr. Matthew Linares for generating some of the datasets used in this case study. And we also acknowledge funding from various sources. Thank you for your kind attention.
Right, so we just heard another quite interesting talk. I thank you very much for giving it here for us. While we are still waiting for some question on the Discord or YouTube, I have one question on my own. I was wondering, during your talk, you were mentioning that within the Voronoi method, you are having the problem that the arrows are pointing in the other direction. And I was wondering whether this is a completely systematic error for the Voronoi, so it could be kind of fixed up by just simply rotating the arrows by 180 degrees, or whether this is more or less random behavior.
It's not random behavior. So the thing is that the Voronoi cells are shifted compared to the, for example, numerical ones. And in this case, particular case, it happens to be that they shift enough to, because these interactions are linear, it shifts enough in 1D to kind of shift the dipole moment in the opposite direction. Based on we have a better explanation in the paper, but like quickly answer is that in this particular case, they shift enough to flip the dipole moment because of the symmetric nature of the data set. So basically, they eat into the other molecule, basically.
Okay, thanks. That's make it more clear for me. Since there are no more questions at the moment, I would like to jump to the next talk, which will be given by Barbora Kozlíková. And she's my long-time colleague at the Masood University in Brno, Czech Republic, where she works as an associate professor. Maybe you also know her as a general chair of EuroVis 2018, that she took place of the general chair. What you may not know is that she was actually the driving force that convinced us to organize the first MolVA workshop 3 years ago. And Barbora is also a head of a visit lab that is a research laboratory focusing on the designing visualization of different application domains. One of the core topics of her research is the visualization and visual analytics of bare molecular structures with a specific focus on the molecular dynamics, simulations, docking, and molecular interactions we will be hearing today about. And as you've seen earlier today, Barbora is also experimenting with virtual reality and its application in molecular modeling and education. And I could continue listening her achievements the whole day, but I'm actually quite eager myself to hear what she has prepared for us in her talk on protein interaction. So without further ado, Barbora, floor is yours.
Thank you. Thank you, Jan, very much for this nice introduction. Actually, today I'm very grateful that we had also Victor as the speaker in the morning, because he quite eased my way today quite a lot, because he was talking about proteins, the basics and the interactions. And that's the topic which I prepared today for the talk. And thanks once again to the organizers for inviting me here. It's really my pleasure to be here with you. So I'll be trying to show you how we are handling with protein interactions, which is quite a complex topic from the visualization point of view. So of course, it won't be a completely exhaustive list of things which are existing around, which the biochemists are currently are having for their disposal. But at least to give you some idea of how the situation in this domain looks like right now, and what are the possible challenges for the future, maybe also for you. So I will start with just a very one small slide regarding molecular visualization itself, because it is one of the oldest branches of visualization, and we are having many visual representations that have been already proposed in the past decades, and they are already kind of a standard. So here is just one example of different types of visual representations of molecular structures. Sorry. Another example could be like a bit of advertisement. It's a paper which we published a couple of years ago with Michael Krone and other colleagues. And in that paper, we were trying to somehow redesign a taxonomy of the existing visualization methods for molecules at that time. So you can check it over there, but I definitely don't go into detail here. And another evidence that molecular visualization is the topic, and hopefully still be the topic, is that we are having quite a couple of different venues where these are dedicated either completely or partially to molecular visualizations. And I can name here EuroVis, visual computing for biology and medicine, and of course this workshop. So it's the right place to be here today. So I'll jump to the topic finally. So why we are dealing with protein interactions, what's so interesting, exciting on them? So protein interactions are basically a key aspect of all the chemical reactions which are happening in organisms, as we've seen in the morning in the talk by Victor, and also they are triggering the changes of different molecular properties and their functions. And these interactions are studied in many domains where they really play a crucial role. For example, protein engineering, drug design, we also seen examples of that, nanotechnology, and many others. And I have here just a small depiction which quite nicely illustrates what actually the interaction can be about. So on the left side, we can see like an image where this small ball represents a protein, and the key is representing some molecule of ligand, which is supposed to interact with the protein. So if the reaction is happening on the protein surface, which is on the left side, it's just basically the key locks to the surface itself. On the other hand, there are also some other approaches or other types of reactions which are happening deeply inside the protein itself. And this is the second case on the second image, where basically I have to enter the key first to the inner part of the protein and then find the right configuration over there. Now, before jumping into individual examples of different approaches to protein interactions with other molecules, I'll try to start with some challenges. I will name 3 of them mainly, which I can see in this domain. And the techniques which I'll be presenting afterwards are addressing some of these or combination of them as well. So we will see. So the first one is related to molecular dynamics. So basically the idea here that the interactions between molecules are happening over quite a long time often. So in consequence, it leads to capturing the simulations of these molecular movements, which can consist at the end of hundreds of thousands or even millions of time frames, which is quite complicated and cumbersome to analyze. So the traditional means of observing the animation of such a movement is not happening anymore, just because of a simple fact, like here in this example, imagine that we are having 100,000 time frames, which we would like to observe in 1 frame per second speed, then it would result in something like almost 28 playback hours, which is definitely impossible for the biochemist to sit and watch the whole time. So there has to be some other way to handle the situation and somehow analyze more accurately, intensely such a simulation. So that's the first challenge. The second one is that within the simulation, within the interaction, there are different molecular properties playing a role. And the biochemists, biologists need to understand them and their importance in these individual processes to somehow decide on what is happening, why it is happening, and what influences a certain function, for example, of a molecule. So these interactions basically are influenced by two main types of properties, let's say. One of them are geometric properties. I just listed here two simple examples like distance, angles, but we've seen these in Victor's talk as well. And more importantly, even there are some physical-chemical properties playing a role there. So we need to take into account the atomic charges, the hydrophobicity of individual amino acids, the force field calculated for the whole molecule, and so on. So all these forces and charges and so on are significantly influencing if the actual chemical reaction can happen or it is impossible. And the third challenge is basically more related to the analysis of such a data, and it's somehow also related to the molecular dynamics simulation, the challenge number one I was mentioning. So basically, it's the importance of these individual parts of such a simulation, but it can be even on different scale. We can have even some other properties which are important in one particular arrangement of molecules and, for example, not in the other, and we would like to know what's the reason of that. So if I'm talking now about the molecular dynamics simulations, then basically we are trying to figure out which properties are crucial for protein function, and we would like to localize these changes, these important properties, when they are occurring over time. I'm calling it an important event here. And you will see that we were taking this concept also in some of our papers, which I will be discussing in a bit. So we need to figure out where some important thing is happening, and this part of the simulation is worth for the biochemist to explore, and the rest of the simulation can be omitted because there's nothing important happening. So what could be such an important event? So for example, it could be the speed of the reaction between protein and other molecule, or it can be a change in the interaction energy. Or more geometric property could be like some significant positional change in the protein itself. And I have here like a small example of that when, for example, I'm having a protein here with consisting of two domains, and this protein basically has here such a hinge, and this hinge causes the opening of the molecule and closing it again. So within the simulation, when we are getting to the situation when the protein is opening, it means that this is the case when it can adopt except some small molecule of ligand which can interact with the protein afterwards. If the protein is in the closed state, then this probability is way less smaller. So what matters even more is that we are having a lot of these parameters, properties, which are describing the importance of individual parts of the simulation of the protein. But even more importantly, what makes the situation more complicated is that the combination of these important events matters even more. So if there is some geometric change and at the same time, for example, some energy peak, then this is even more important than only a geometric change, for example. So all these things are playing a significant role for the biochemist to understand the properties and functions of proteins and interactions with other molecules. And these have to be somehow understood. And that's why visualization comes into play, because it really can give them a nice overview of different properties, parameters they are interested in. So in the rest of my talk, I would like to show you different examples of the existing proposed representations of interacting proteins with other molecules. And I decided to divide it into three main parts. In the first part, I will show a couple of examples of protein-ligand interactions. Then there will be smaller subparts, part 2, protein-protein interactions, and then protein-solvent interactions. So let's start with the first one, protein-ligand interactions. So here, basically, the idea is that we are having a protein structure, then we are having a small molecule of ligand, and within the simulation, this ligand is somehow, this is like very brief illustration, but it's somehow floating around the protein and is trying to find its way into the inner part of the protein itself. This, if you are a bit familiar with biochemistry, it resembles molecular docking. So basically here, what happens at the end is that the ligand is following a certain trajectory, and it's worth to explore such a trajectory and understand how and why this ligand behaved as it did within the path along the trajectory. So at the end, what we can get is something like this. So you are basically having a lot of trajectories which are floating around the protein and also in the inner space. And it's worth to explore and understand which of these trajectories and which parts of these trajectories are actually interesting and important for the biochemist, because in this representation, it's probably not very meaningful to observe basically anything. So for this purpose, we designed a couple of years ago with Katka Furmanova a tool which is serving for exploration of these ligand trajectories. And as a first part, we were trying to analyze and define with the biochemists what could be this potentially interesting and important events which is worth to capture, observe, and track. So I'll just show an example of that so you are having an idea of what I'm talking about here. So one possible property is that we were looking at the amino acids which are surrounding the ligand along the when it traverses through the along the trajectory. So another thing would be the amount of free space which is around the ligand in that particular time step. Another property was when the ligand is moving, then some of the amino acids which played a significant role within the transition process is disappearing, like this amino acid number 1. But on the other hand, there are some other amino acids along the trajectory which are starting to influence and play a role within the process of transferring the ligand into the active site, which is the black dot on the right side. There are some other properties, for example, the direction, if the ligand is traveling towards the active site or vice versa towards the surface of the protein. Another parameter which is worth to observe is the speed of the ligand, how fast it goes through certain parts of the trajectory. Quite opposite, there is something which we called stuckness, and it's a parameter which tells you when the ligand somehow got stuck for a certain period of time, and it's worth to observe what was the reason of this event. And then, of course, the distance, which it still has to travel to a certain point, in this case, to the active site. So these were all the parameters which we were trying to observe and analyze. And at the end, we came with the tool where I won't go too much into detail. And if you would like to know more about that, you can check the paper. But basically, the idea was that we were creating a visual analysis tool consisting of a couple of linked views, where on the top left part here, you can see just the part of the trajectory which is explored here, and you are exploring different of these properties which I was showing on the previous slide. And you can explore visually individual parts and trying to understand how the ligand behaved along this particular trajectory. And another very nice example of visualization of molecular interaction forces was presented again a couple of years ago by Pedro Hermosilla and his colleagues from Barcelona. And you've actually seen this image already in the morning in the talk given by Victor, because he was also collaborating on this tool. So here we can see very nice 3D visualization of ligand, which is approaching the protein, where the authors were using clip planes to really get insight into what's happening in the interacting space between the ligand and protein. And more importantly, they were also showing here, like by small arrows, like that these individual parts of the ligand are actually now somehow interacting using different types of forces with individual amino acids or atoms of the protein itself. And the tool was accompanied with this, it looks like a map, but basically it shows the flattened view of the ligand and its interactions at the particular moment with other parts of the protein, which are here like floating around in the space, in the air. I was also somehow collaborating with these guys in 2019 with Pere Pau in Barcelona and his student. We were designing a tool for visualization of large molecular trajectories when we were having a case where there was a protein, and in this case we had 3 different ligand structures that were trying to interact with this protein. And we were observing within the simulation when these ligands were actually approaching the inner part of the protein, in which parts of the time, and so on. And we were measuring different parameters here. In this case, it was velocity, Coulomb energy, and van der Waals energy. As we were having 3 ligands, then here you can see 3 individual plots. For each of the ligand, there is 1 plot. And one important thing here is that, of course, you can see the animation of the movement if you launch just the playback of that. But more importantly, these plots are serving as a navigation to some important, interesting parts which are worth to explore by the user. And this is done mainly by this dark background of these graphs, which are signifying that something interesting is happening there. For example, the ligand is approaching the active site. And at the same time, you can see how the other ligands were behaving, how far they were from the active site, for example, and so on. So for the exploration process, this was quite a powerful tool. Another example is from Robin Skonberg, which was presented at this workshop a couple of years ago. And it's a tool called VIA-MD. And basically, this tool presents a tight integration of statistics, plots, and visualization of molecules. In this case, we are having a tubular structure, which is in the central view, and a couple of ligands floating around the tube. And the important event here was that the ligand was approaching the tube and basically changed its configuration and started to interact with the tubular structure. So again, you can see a combination of different types of plots for different properties which are interactively linked together. And additionally, they also added something like a Falk-based representation for a selected ligand. So you also got a glimpse of how the ligand was traveling along the MD simulation over time. So that's another very nice additional feature. There is another approach which was published in 2018 by Pere-Pau Vázquez, and this time he was again focusing on interacting ligand and protein, but this time he was trying to use very abstracted representation. So basically the protein itself is represented by the circular view, and you are having here individual amino acids encoded. And when you would like to explore the interaction of a ligand with this protein, then the ligand is positioned into the center of this circle, and then you are having different types of connections and some other information which gives you the idea about how the ligand is actually interacting with individual amino acids of the protein. But if you check the paper, you will see way more examples of what is possible to, what can be seen in this visual representation which he designed. Going a bit to the direction of utilizing techniques from computer graphics in molecular visualization and looking at the interaction of a ligand with protein from a slightly different perspective. This was the work again of Robin Skonberg and his colleagues in 2015. And this time they were using diffuse interreflections and ambient occlusion technique to highlight how and where actually the ligand is interacting with the protein itself, with its atoms here. So these, let's say, the interreflections here are showing the intensity of how much the individual atoms were participating in the actual interaction, and it's based on the calculation of the distance and ambient occlusion. So the results were very appealing and very nice. Our contribution to solving one of the challenges which I was mentioning at the beginning, when we would like to navigate the user to some interesting part of the molecular dynamics simulation where something interesting is happening based on some important event, we designed and proposed a tool which was presented in 2019. Jan Byška was the author of this tool with his colleagues. And here, basically, the idea was that for the molecular dynamics simulation and the input, we were having different properties and parameters, which were measured for the whole empty simulation. And as I mentioned, the combination of these properties is even more important for determining what's important and interesting to observe. So basically, we were trying to combine these individual properties to something which we call an importance function. And based on this function, we were influencing two things. One was the focus area, so where this important event happened. Then we localized spatially this area within the protein, and this was depicted in more detail. The rest of the molecule was shown just a cartoon as a context. And the second thing which we were influencing by this is the playback speed of the molecular dynamics simulation when animating that. So here is the example of that. So here you can see that when launching the animation, when we are getting to some peak in this important function, then the animation is slowed down so the user can really observe in more detail what's happening there. And of course, if there are some unimportant parts of the simulations based on this function, this can be completely skipped. So we are saving the time I was mentioning at the beginning that this is an issue. And as one of the last examples from this protein ligand category is an example of molecular docking, which we were also working on basically last year. It was presented or already almost 2 years ago, it was presented at the VCBM conference. And here the idea was that we are having results of a molecular docking tool, a computational one, and we are having ligands which are traversing through this trajectory to the active site, and the users would like to compare the trajectories, their speed, orientation, and assess also the energy peaks, and then assess if this is actually a feasible simulated docking or not. And for this purpose, we created another tool, which is consisting of a set of linked views. The main part, of course, as usually, or very crucial part, is the 3D view showing these individual ligands interacting amino acids around. But we are also having a couple of plots here, which are showing the energy peaks for these ligands when passing through the trajectory, and also like this flattened view where in these individual parts, when the ligand is actually located right now, we are seeing a list of amino acids which are forming or like surrounding the ligand in this particular moment. So I hope that yeah, having the animation of this. So basically, if you launch the time, it means that the ligands are traversing through their trajectories, and you can see them their mutual orientation, and you can also observe individually how they are behaving here, even in this flattened view and so on. So it was quite nicely tailored for this type of tasks to explore different trajectories which are calculated using some docking tool. So the second part I would like to mention, and it will be way smaller, is about showing and conveying the interactions between two or more proteins. So basically here we can really handle two or even more protein structures which are interacting together. Here the difference, the main difference is that the interactions are basically always happening on the surfaces of these proteins. So as we've seen before, the case when ligand was traveling to some inner part of the protein itself, this is not the case here. They are really interacting on their surfaces. What is important here is the interaction part of the proteins, which we call like contact zones between the proteins themselves. So this is something which is of utmost importance to determine if this actual interaction is possible or not. And if you are using some of the existing tools for the calculation of possible solutions, possible configurations of, for example, two interacting proteins, you can use tools like HEDOC, PyDoc, and so on. Then you can get a list of even hundreds, or in some cases we are also experiencing like thousands of possible configurations, which should be then explored and assessed by the biochemists for their biochemical feasibility, if this is actually something which is possible to happen or not. So that was the input point for us when we started to think about how to ease the life of the biochemist in this context, and really filter out those configurations which are not important, interesting at all, and let the user to explore only a very small subset of the configurations in detail in 3D. And for that, we designed a tool which was presented at BMC Bioinformatics 2018. And basically here we were having a set of input configurations of two interacting proteins from some computational tool, and using an abstracted representation, a simple matrix, we were trying to filter out those configurations which from the biochemical, from the opinion of the biochemist who was exploring this data set, didn't make any sense. And I will show on the next slide how actually the matrix looks like and operates. And then we provided the users with a set of views where they could observe individual properties of the contact zones and so on. So I will just very briefly show you how this works. So the first part was the matrix, when we were plotting these two proteins on these two axes of the matrix. And what happened was that when the two amino acids were in a proximity for being in the contact zone, then this was here observed as a single cell, which has a more saturated color. So the user could easily select that if he or she knows or wants these particular two amino acids, for example, to interact, then the easy way would be to select this cell. And then basically those combinations, those configurations which are not containing this combination of amino acids in the interaction proximity were filtered out automatically. So in this way, we are getting smaller subset of proteins, which can be then explored further. And this is already in 3D, because the 3D really here plays a crucial role. And we designed representation when we merge all these remaining configurations together. And after that, like there is one protein which is reference one, but I'm not going into much detail here. But more important thing is that if the contact zone is in between two proteins, then it's not visible. And that's actually the part which is the most important and interesting for the biochemist. So that's why we designed something like an exploded view, where we were like putting remote to more remote distance these proteins which are interacting with one of the reference one. And then even more importantly, for a selected pair of proteins interacting ones, we were using this open book representation where the user can actually really see inside the contact zone, and using different coloring you can understand the properties, the distances of individual atoms, amino acids here, and so on. And the last part, which again I won't go into detail, was something which we call the list view, where you can really observe in very detail for these individual configurations the amino acids which are playing role in their contact zones, and like which ones are missing in which one of them, and so on. But this I won't explain in detail, but in combination with the 3D views linked together, this worked really, really nicely and was presenting quite interesting results. Another issue here is that quite often we can also work with multi-complexes. So it means we are not satisfied only with two interacting proteins, but we can have a set of them, like in this example here. So it's highly combinatorial task, because you can have many combinations of how these proteins can interact, and these interactions are even not like paired ones. So one protein can interact with more proteins around itself. So again, we can get hundreds of possible configurations which we need to somehow explore and assess their feasibility. And the automatic approaches are often failing, because there are really many parameters and features which need to be taken account for deciding if this particular configuration is feasible or not. So again, same story as in the previous case, it's impossible to browse them one by one. So we need to come with some solution. And simple 3D view, again, is not sufficient. As maybe you can guess also from this image, you can see that the contact zones, again, are in fact hidden inside the protein complex. And it's impossible to observe this without any further visual aid. So for this case, Katka Furmanova and colleagues designed a tool which was presented almost 2 years ago and published at TBCG 2020. And here again, I'm not going into details. If you would be more interested in that, I will refer you to the paper, because the explanation of these individual views, and you can see that in this case, we are really having way more than in the previous one, because the complexity is increasing. Then you can just check it in the paper itself. But basically, the idea was overview first, and then going into details and filtering out again those configurations which are not feasible at all. So in this case, this graph structure here is representing these single proteins which are forming the complex, and the connections are showing how often they are interacting within the calculated data set for all possible configurations. And based on this information, the user can select and filter the other views as well. And now I will quickly jump to the third category, which will be about protein-solvent interactions. And basically, what I mean by solvent here, it's the environment where the protein actually lives. So it's not in vacuum, it's surrounded by some other small molecules, and usually we are talking about water molecules. So we can, from the simulations, get quite easily example like this. So basically we are having a lot of water molecules floating around the protein, and when visualizing this representation or using the very traditional way as it's visible here, then basically we cannot or we can very barely see the protein inside. And if you even imagine that all these water molecules are moving within the simulation, we are basically getting a soup of something which doesn't have any particular meaning, and it's really hard for the biochemist to understand and decide which of these water molecules are playing some role in such a long simulation, because it's not just about floating around the protein, but actually some of the water molecules are entering the inner space of the protein, and then they can, for example, fill some void space inside, which is then not possible, which cannot be afterwards used, for example, for a ligand going through the trajectory as we've seen a couple of minutes before. So the role of the water molecules is very important, but it's also a very complicated task, as we can see here. So one example which was designed for exploration of the individual path lines of these water molecules was presented by Gillmann and her colleagues in 2008 already. And basically, here the idea was somehow to simplify the trajectories which were extracted from the simulations. So on the left side, we can see all water molecule path lines which were extracted for a certain small area within the protein. And what the authors were designing was that they were trying to extract something like, they call it main solvent paths, so some important parts of the trajectories, and simplifying and smoothen them. So basically you are having better idea about the trends of the movements of the water molecules instead of individual trajectories. And also the coloring of these trajectories had a certain meaning here. We also were trying to contribute a bit to this category and analyze this float of many water trajectories around and inside the protein structures. So with Victor Watt and colleagues at TU Wien, we were designing a tool where basically the input looked somehow like this. So only for a small subset of the molecular dynamics simulations, when we were taking all the water trajectories, then we finished with such a hairball, which is visible here, and even inside is a protein which is completely invisible. So this information is basically useless for the biochemists, and in fact what they were interested in were only those water molecules which are somehow interacting with the inner space of the protein. So only those waters which are entering the inner protein space should be tracked and observed. So even when we filtered out all these waters which are not fulfilling this condition, we ended in something like this. So basically here we are having quite dense concentration of trajectories of waters. Again, I'm not getting into detail about the coloring, but what I would like to show here is that basically even in with such a small subset of water trajectories, we are still having only basic information, and the representation of these individual trajectories still didn't make sense, as we've seen also in the previous case of Gillmann and colleagues. So in our case, what we were trying to do was that we designed an approach where we were replacing these individual trajectories with isosurfaces, which were showing the distribution of the probability, how often the water molecules are occupying a certain space inside a protein over time. So basically, this representation could be interpreted in that way that, for example, if here in the inner part we are observing this red isosurface, it means that here there was a highest concentration of water molecules over the molecular dynamics simulation. So, and in this way, we could very nicely and easily see like the aggregated information about the appearance of individual water molecules, even through the whole dynamic simulation in one certain one single snapshot. So I'm getting slowly to the end because I'm also running out of time. So to summarize my talk, I hope that at least to a certain extent, I convinced you that the visualization and techniques which we are designing in molecular visualizations are substantially aiding the exploration process of the molecules and interactions between them. And with the increasing complexity and the length of the molecular dynamic simulations, as we were seeing at the beginning, the visual support is really crucial to have and to provide the users with, because without that, it starts to be really impossible to somehow understand the behavior of the protein and interactions between them. And of course, there are some open challenges. I will be mentioning basically those which are of our particular interest these days. And these are those which are connected to the detection of these important parts of the MT simulations. So we've seen some examples that we or other colleagues are already trying to handle this complex problem and trying to navigate the user to important parts of the simulation. But I believe that there is space for something which is floating around the visualization domain in many areas, and it's basically artificial intelligence. It sounds more maybe like a buzzword these days, but I truly believe that if we, and of course in combination with biochemists, we are able to define, at least to a certain extent, which parameters, which properties, which values of these parameters and properties and combinations are important for certain features, phenomena happening in the molecular dynamic simulations. This could be nicely trained by some network and then reused for some other simulations, because it's not just about single long ND simulations, but nowadays we are capturing ensembles of hundreds and even thousands of simulations to confirm or deny some hypothesis. And this becomes really a huge amount of data and big problem. And of course, if we are having something like this, we are having the individual parts detected, then we need to provide the user with some visual cues how to explore these individual parts in the best possible way. So some visual navigation to these parts is something which is partially solved, but there are still many, many open challenges. And we are looking forward to work on this right now, basically. So with this, thank you once again very much for having me here, for inviting me. I would like to thank also the collaborators from biochemistry or the visualization domain as well, who are contributing to our papers, which I was presenting here. And if you have any questions, I'll be very happy to answer them now or later on Discord, or catch me anytime on my email address. So thank you very much once again.
Laura, thank you very much for such an interesting talk and a great overview of the techniques which are out there. Your talk actually generated quite some questions already, so let's dive right into them. Alexei is asking whether you are using or taking into account the force field parameters when you are exploring the ligand trajectories.
That time when we were designing the particular tool I was showing, it was not the case. But of course, we realized very soon that this is a big issue, and without the simulation of the force field, this actually won't be so accurate and feasible. So this is something which we are trying to integrate and address, but it's not there yet. But it's a very important part of that. You are right.
Okay, thank you. I would also add that I think, or maybe you correct me, but isn't it true that the force field is somehow included into the MD simulation computation? So it's somehow within the data also inherently.
Yeah, you are right. If that's a very good point, Jan. Thank you very much. And it's really very nice to have the chair of this session being my collaborator as well, because he can help to answer the questions as an author of many of these tools I was presenting. So yeah, you are very right. But you remember that we were also a couple of times discussing that really having the force field somehow visualized also would be an interesting thing to do and give the users to their hands.
That's definitely true. So Bjorn is actually asking what is your take onto the VR-driven approaches when it comes to the molecular analytical context? And also Martin Fox is adding, what about the haptics as well?
Yeah, there are certainly fields which I didn't touch at all, because also I had a quite limited time. And you are very right, like virtual reality and haptic simulation in particular were very interesting for the exploration of interactions between protein and ligand. So I remember that a couple of times there were attempts to simulate with force feedback the transfer of ligand to the active site and really feeling the forces which are preventing you to get inside. And this was really very impressive, let's say. So you could get the idea how the ligand actually feels. So it was really, really important. And virtual reality is definitely the direction. And we are also heading there a bit. You've seen a bit in this session as well that we are touching this, not yet from this interaction between molecules point of view, but it's certainly something which I think is a direction where people should devote time and effort, because it's more and more available, affordable, and also interesting, and gives you new perspectives.
Thank you. I hope that answers the Bjorn's question. There is also one more from Alexei. He's asking that whether for the solvent tracking, whether you can track how the water molecules are arranged around the protein surface.
It's basically, of course, you can do that. You can track this. For the particular case which I was showing and was the task for us from the biochemist at that time, like these water molecules which are like interacting or like floating around the surface of the protein were not so important and crucial. And basically, as there were really a lot of them, then it was even more beneficial to filter them out, because then you can really have a better view on the protein and what's happening inside. But it really depends on the task. So if your task would be that you would like to see, for example, how the protein surface and in which certain time periods is occupied by molecular structures, if they are like interacting on the surface, then of course this would probably need slightly different visual representations than we designed, but it's definitely interesting and doable.
Mm-hmm. And Bjorn is asking one more question. He's asking whether did you look into visual analysis of vesicle interactions?
Well, not by our hands, let's say. We didn't touch this topic, but it's thanks a lot. This is like actually very, very good connection where to see go and be inspired, because there are many things happening there which could be taken into account here and used here as well. So definitely yes, thank you.
So I think that was the last question, if I didn't overlook any. But if you have any more questions, please feel free to write them into the Discord or YouTube. Bara will be hanging out with us for the whole day, so I'm sure she will be happy to answer them later on.
Yes, even for the whole week, so anytime.
And
thank you very
much. That, thank you very much as well. With that, I think we can jump into the closing remarks. All right, so we arrived to the end of the MolVA this year. I promise I will not keep you away from the lunch for too long. I just want to somehow summarize what we had today and provide you with some important information for the future. So we have just seen one of the invited talk given by Bara in the morning. We also had a very nice talk by the Victor. Together with 5 additional papers we had today, so 4 was full papers and 1 short paper. I think we had quite some interesting content. As you may know, the 4 full papers were already published within the Computers and Graphics journal, which was kind of an experiment for us this year. And as we promised at the beginning, what we do is that we run this special section on molecular graphics in 2 kind of parts, so to say. So first, we invited the papers at the beginning of the year to submit, and those papers were presented today. But in the second part, we still are having the open call, or will have an open call very soon for the extended version of the short papers which were published or presented today. And this will also include some new submissions. So if you are interested to publish some work within the molecular graphics and molecular visual analytics, we are happy to inform you that there should be still some chance to get your paper published. So look for more information, which will be coming soon on our web pages and through the mailing lists. And with that, I would like to thank you as well for being here today with us, for watching all the interesting talks, and I hope we will see you next year, hopefully this time in person. And if you have any questions or any suggestions for the topic or changes for this workshop, please feel free to contact us on our email or just visit our webpage and leave some comments there. So thank you very much. And with that, I'm saying goodbye.